Sridhar Tayur, who is the Ford Distinguished Research Chair and University Professor at Carnegie Mellon's Tepper School. He's a very wide-ranging individual with interest in many, many areas. And so we're going to get a chance to see some of the latest research that he's done with his co-authors here. Also a founder and CEO of SmartOps. He created the field of quantum integer programming, 2018, an Informs Fellow, and many other awards. So I'm going to sort of pause here and turn over the presentation to Sridhar.
Thank you, Doug. This on? Okay, thank you. Everyone hear me fine? All right, thanks for coming. First, I want to thank Doug and the editorial team for accepting this work off process. I did not know that you have to be invited to publish in tutorials of OR. So Vikesh and I created this. Vikesh was my postdoc. He has his PhD in physics, so he's a real physicist, theoretical physics. His advisor is Bob Griffiths. If you're in theoretical physics, you know who Bob Griffiths is. And he did a postdoc with me, and we said, I want to do one part which is research. I'll mention it briefly in quantum communications. And then I thought it would be nice to build something educational. And I said, what is an intersection between theoretical physics and operations research that makes sense? And he said, semi-definite programming occurs everywhere in quantum information science. I said, I think I've heard of semi-definite programming, so why don't we connect the two? So Vikesh is now at IBM TJ Watson in their quantum group, and I think in September that group, which has some of the famous physicists, theoretical physicists, won the breakthrough prize for theoretical physics. You know, Charles Bennett and those names. So he's a theoretical physicist of sorts. So once we wrote that, we said, where should we publish this work? And the feedback was, oh, tutorials in OR is kind of the place that you're trying to hit. So I think I wrote to you, Doug, and I said, by the way, we have this. And then when I went to the website, I found that it was by invitation only. So I said, well, I guess I've not been invited, but here it is. But thanks to Mabel and you and others, you decided to add it into the program. So that's kind of a little bit of a background. Okay. So I think the question is, why do quantum information science? Which actually begs the question, what is quantum information science? But let's kind of start with that. And importantly, you know, what can my PhD is in operations research from Cornell, and I used to do some mathy stuff for the first few years. Then I decided I want to do something practical, and as Doug mentioned, I started a software company. I was the CEO for a while. SAP bought us, and I think there are 700 companies running about $1 trillion of business off my code. And then once I sold that company, I thought I want to do anything but supply chain management. Just because I think, you know, when you spend 10 years doing supply chain academia and 10 years selling software, and your total life horizon is, you know, some order of, you know, 20, you don't want to be doing just the same. So I got into something called healthcare operations, and randomly got into organ transplants. Came up with a second company called OrganJet, where I wanted to democratize Steve Jobs and get people kidney transplants, even if they were not billionaires. I made it up as a whim. Okay, you see a pattern here. Okay, but it turned out that the world loved it. UNOS's president at the time, John Roberts, said this was the most deceptive idea in organ transplantation in 30 years. Then Harvard decided to write a case on it. It taught in like 50 to 60 universities around. Then Obama called me to the White House when he was the president, along with Al Roth, who had just won the Nobel Prize a couple of years earlier. Then the World Economic Forum added me to their speaking circuit, where I speak every year to help people think about how to use business thinking to solve social problems. So, I did 20 years of very hard work that, in my view, went largely unrecognized because people never heard of supply chain until the pandemic. And so, if anything, COVID brought up the word supply chain, and people now know supply chain. I remember when Trump was president, he would say supply chain many times. I don't know whether he understood it or not, but the fact that he said it meant a lot of people heard it, right? But it's almost like when I started OrganJet, I got all the kind of the fame and the credit for not putting much effort at all. So I view that as all the inventory built up got paid into that. So I've been doing that for a few years. But around 2017, I decided that's enough of organ transplants. I did a couple more things. My student actually is up for 4 awards this conference in split liver transplants. And so I thought, enough of healthcare, enough of organ transplants, I want to do something else. I was drinking a nice martini at a sports bar, and I thought quantum computing sounds good, right? And so I decided to start on a whim and say, let me do quantum computing, right? What is quantum computing? In 2018, there was a call. 2017, there was a call from NASA and USRA, that is University Space Research Association, saying that they have bought a D-Wave machine, which is sort of an Ising solver, and you get 100 hours for free if you write a 4-page proposal about what you want to do with it. So I wrote a 4-page proposal saying I want to explore the use of quantum computing to solve integer programs, because integer programs are hard. I think they were very amused because mine was the only business school application that was brought into NASA. I think they never knew that there was something called a business school. Usually they get chemists and physicists and maybe some errant electrical engineers who would rather be physicists. And suddenly they get a business school and they say, who's this business school guy? And anyway, so we became good friends since about 2018. In fact, David Bernal, who was a PhD student, was an intern in their NASA Feynman Academy, I think in 2019. In 2020, I wanted to teach a course called Quantum Integer Programming, and NASA actually paid money so they could take my videos and make it part of Feynman Academy. So since 2020, I think our course, which was co-developed with David and one NASA person, is actually part of the Feynman Academy core class. And then 2021, I started looking at hardware, and I thought, oh man, these guys are not even close to actually building a quantum machine. Although I'm doing this for fun, I wanted to be somewhat, practical. So I started making fun, actually, of IBM and Google, saying that, this is a total waste of money. This is what happens when you have money but no imagination, etc., etc. And my alternative was that you can do quantum-inspired semi-classical computing. Okay. Anyway, so I have a blog where I randomly shoot from the hip. So I've been doing that. Imagine my shock when in 2021 DARPA announced a $60 million program saying that quantum computing may be many decades away. We should do quantum-inspired classical computing. Okay. And anyway, long story short, we got a $10 million grant to build one of those machines. So it could be one of those things where I started with a whim, but it might actually become a thing. Okay. But as I thought about what I could do to bring more people in OR and computer science in, I thought this could be one way of bringing people who already know semi-definite programs, people already good in mathematics, but don't know quantum mechanics and quantum information science, because it's kind of a big jump to take care of this. Are we good? Okay. Uh-oh. All right. Okay. So imagine my surprise when after we agreed to give the talk here and so on and so forth, not only did the breakthrough prize go to the theory guys at IBM, The experimentalists got the Nobel Prize in physics, which is this is it. I mean, you don't get a better prize than this on Earth if you're a geek, right? And so woke up one morning and they say, wait a minute, they're actually giving the prize for quantum information science. This thing is real, right? And so I think I wrote to you, Doug, and I said, what a world, right? And so what can we do? I think we know how to do computational work, and we know how to prove worst case bounds. The question is to formulate problems in quantum information science in the language that we know, which is semi-definite programs, and apply the skills that we have in solving SDPs either computationally or writing bounds on it, so that we can actually inform quantum information science. So what I'm saying is, I'm not using quantum to solve OR. I'm saying OR can help quantum information science. Okay, that is, we can use our skills to help actual theoretical physicists because they don't think like us. Okay, so to me, that is the kind of the opportunity here. While we wait for quantum to help us, I think we can help quantum, and then maybe quantum can help us. Okay, that's. I think quantum computing has the highest buzz in the world. Okay, wherever you go, JP Morgan Chase is investing in it. I don't know why, right? And IBM is everywhere pushing quantum. Google CEO was on the cover of Fortune magazine with that machine, I think in 2019, right? So I think the real quantum is far away, but I think a bit closer to things that could happen maybe in quantum communications. And I think something that is potentially right now, right here, is quantum sensing. Okay, just to give you like an amazing example of quantum sensing, have you heard of LIGO? LIGO stands for laser interferometry or interferometer gravitational observatory, right? So it's up there somewhere in the sky, right? I think, right? Or is it on the ground still? The next one is going to be in the sky, right? Where they want to measure the gravitational waves due to some supernova explosion. I mean, imagine the precision, and then show that to 9 decimal places, Einstein's prediction of gravitational wave is correct, and that won the 2017 Nobel Prize, right? And to improve that LIGO, they now have ways of looking at all the photons that hit it and somehow cancel that noise through entangling it negatively, so they can measure gravitational waves every like 16 decimal places. It is mind-boggling, the kind of scientific precision that's out there, and you say, what is the mathematics behind all that? Is quantum information science. Okay. Now, of course, the practical application of quantum information science that has helped DARPA find money and the Department of Defense find money is because it wants to sense nuclear weapons. It wants to sense underground submarines and so on and so forth. So quantum sensing, just to give you a sense, I think has many more practical applications. It's also much closer to practice, and just to give you a sense of things. So I started this group. I first called it Quantum Computing Group, and then as I worked more and more, I decided quantum computing was too narrow, and so it's now relabeled as Quantum Technologies Group. Okay, and thankfully I renamed it just before I sent you the paper, because now the paper says Quantum Technologies Group. Right. So I'm a very practical man. So I usually work with people with money. And so hedge funds and stuff. But then there are very, very nice problems in cancer genomics that can be reframed as very hard problems in integer programs that I think can again benefit from this kind of thinking. So it's a very, very broad application basis. Then I got into hardware, and then some of the algorithms that's out there, and then some recent work in quantum communications. So you'll see a website there. If time permits, at the end, I'll click on it, and we can walk through some of the work being done. Okay, so just to give you a sense that this thing is real, and people like us can contribute. Okay. So why did I choose the title 5 starter pieces? I first wanted to be 6 starter pieces. Why 6? Who is the most famous American physicist who wrote for common man? Richard Feynman. He's got a book called 6 Easy Pieces, and then he's got a book called 6 Not So Easy Pieces. So I wanted to be 6 starter pieces. After a while, Vikesh got tired and he said, hey, Prof, can we make it 5? so I said, fine. So it became 5 starter pieces. Okay. And the second thing I wanted to bring up is in the thing you'll say quantum mechanics, the bare minimum. That is, you can't know less than this. Okay, so I've tried to strip out everything. Okay, anything less than this is like a minimum viable product in software. Right? Smaller than that, it is not a thing. Okay, and where did I come up with the phrase the bare minimum? Who is another guy today who is a famous physicist, no Nobel Prize yet, who writes for the common person? Stanford professor. Bearded guy, bald. There's Lenny Susskind, okay, and he's got books called Quantum Mechanics, Classical Mechanics. What is the subtitle? The Theoretical Minimum. So basically, to honor Feynman, I wanted 6, but it became 5, and for theoretical minimum, I made it bare minimum. Okay, but you'll see in this, you can't know less than this. So first thing I want to say is, it doesn't have to make sense. Don't even try to interpret it. Some people in the 60s and 70s went to Zen and thought about Buddhism, and some people then thought, the Indians in the Vedas had already done it. Don't go there. No. I think it was a Cornell professor, a Mermin or something, who said, just shut up and calculate. Okay? It is a mathematical framework with matrices that works remarkably well. Okay? Just until it stops working, just use it. So I'm going to take this perspective that this is about matrices. Okay? And so how many of you have seen linear algebra in your life before? Okay? How many of you have seen complex numbers before? How many of you have seen probability theory before? That is all you need. Quantum mechanics is linear algebra with complex variables, with certain things interpreted as probability. That is it. If you strip out all the noise, thousands and thousands of books and hundreds of pages, that is it. That is it. And it boils down to this saying, you have a column vector in d dimensions. In fact, take a 2-dimension qubit. Okay? Here's some language you should know. There's something called a computational basis and this thing called this ket notation. Okay? Again, you start reading physics books, it scares you. Think every time you see a ket, you think of a column vector. When physicists says it's an operator algebra, it means matrices. When they say it's a poly matrix, it's a 2x2 matrix with some i's in there. I mean, I used to think it is economists who took nothing and made it a lot, but now I see that they're incomparable to physicists who took even less and put more stuff around it. I mean, if you strip it, what I'm saying is, if you strip through this, there ain't much going on. Okay? Now, what happens is, every state is some C0 times 0, which is a column vector, and C1 times that column vector, where C0 and C1 are A plus IB. Okay? Right? You are already in a 2-2 space. That's what I'm trying to say. Okay? So then, any state, at least in a 2-dimension, can be written very simply like this, and this is a qubit, a quantum bit. Okay? We know bit from Shannon as It's either 0 or 1. Qubit says you can be in a superposition of 0 and 1, which means that you can be C0 times this ket 0 plus C1 times ket 1, where C0 and C1 are complex numbers, with C0 squared plus C1 squared equal to 1, because C0 squared is viewed as the square of the amplitude is viewed as probability. Okay. Now, creating physical qubits and manipulating them is what quantum computing is. Now, there are innumerable choices for physical qubits. Every day you go into archive, you will see some European dude, some Chinese group, right, with their own qubit. I mean, oh my God, there are so many qubits. You're like, no, just make one work. Okay, right? The most commonly used qubit, which is these ugly, ugly machines that you see, is cooling something down to nearly 0 Kelvin, where things become superconducting. Electrons become pairs called Cooper pairs and start behaving like bosons. And you can manipulate them going clockwise or anti-clockwise using microwaves, and you can make it as if it is a superposition of clockwise and anti-clockwise, and that is a physical qubit that is inside IBM and Google. My criticism was, it takes so much effort to create this, how is it scalable, blah, blah, blah. The opposite being, can you create a qubit at room temperature? And then optics, photons, give you that possibility. So, in your mind, you can think about qubit as this super cooled, it's called dilution refrigeration or something like that, extremely expensive and so on and so forth. Or you can just say, hey, can't you manipulate polarization, in an optic and do it, okay? But that's kind of physical realization of a qubit. Okay. You can represent a qubit in a sphere where you have an angle away from that plane, right, and into the plane, and that is called a block sphere. Okay. So, again, how many of you remember trigonometry from high school? Sin theta, cos theta plus cos theta. I mean, these guys, this is all that, right? You open a physics book, this just sin, tan, hyperbolic cos, tan, and so on and so forth, because they're working in polar coordinates. Okay. Why is that even directly something you should expect? If you write a complex variable a plus ib, what is its representation in 2 dimensions? You can draw a circle, right? You can have one real axis, one imaginary axis, and that circle will tell you, right, where that complex number stays, right? And now just make that into a cube, that's a qubit. So, what I am saying is, you take your high school trigonometry, which is typically done in 2 dimensions, make it 3, right? We all know linear algebra, but we always worked in reals, right? We are always in Rn, make it Cn, you are doing quantum mechanics. In fact, it is simpler because there are further restrictions on these matrices. I'll come to you in a bit. So, superposition means you can be on ket 0 or 1 simultaneously, and what happens is you manipulate not the zeros and the ones, but the C0 and the C1. Okay? You take the superposition C0 and C1 and you manipulate that over time, and at some point you are going to measure it. And if you did it correctly, the end C0 prime squared will be the probability of finding 0, if that's what you want, or C1 prime squared is the probability of 0.1, and if you do it correctly and you want to find 0, the algorithm will take, let's say, a 1 over square root 2 and 1 over square root 2 start, because it's a half-half start, and make it towards a 1-0 finish. So a quantum algorithm starts typically with an equal superposition state, which says you can be anything, and then through a sequence of matrix manipulations, typically unitary matrices, you will transfer that C0 and C1, we start at 1 over square root of 2, into an end state C0 and C1, so that when you measure it, you will get the right answer with very high probability. That is what is going on. A quantum algorithm is a set of matrix operations starting from equal superposition state. That's what it is. Okay. The excitement was a fellow called Peter Shor showed that you could do prime factorization in polynomial time through such manipulations, and that was a result because classically we don't know if that's possible. We don't know it's not possible, we just don't know if it's possible, but quantum it is possible, right? Then suddenly people thought, wait a minute, all the RSA codes that exist, right, for cryptography is based on prime factorization being hard, and now suddenly you're saying it's not that hard, because in computer science not hard means there is a polynomial time solution. So the question is, if you have a quantum computer, then you can break it, right? And that's when suddenly DARPA and the DOD and the Chinese and the Iranians and the Russians got excited, right? In reality, it is still very far away. So nothing's going to get cracked anytime soon, but I'm just saying that's kind of the history of what is happening here. So if I was going to write a physics textbook today, and I think this is how Susskind opened his quantum mechanics text, his book, I would start with spin. Spin is the quintessential quantum mechanical thing that human race did not know of before 1920. Okay? Sometime in 600 BC, some Indians were running around and they found something we call a magnet. Okay? 400 BC, same thing. Some Greeks were running around and they found a magnet. From about 500 BC to 1925, the human race did not know how in God's name does this magnet work. Bohr actually showed a result that classical physics cannot explain ferromagnetism. What was needed was something called the Ising model, which is based on spins. And the thing was, there are these things called spin which can take only two values, a plus or a minus. Now, one more thing I want you to learn about physicists. They are very bad at naming things. When you think about spin, you think you are spinning like a earth, like a top, it's like a continuous thingy. No, spin is a two-valued discrete thing. You say, why in God's name did you call it spin? Somebody called it spin because it reminded them of angular momentum, evidently, and it became a spin. Okay? So again, when you read physics books, please do not read the English like a normal human being. Okay? In the beginning, when I read about spin, I thought maybe they were simplifying it for me, but after reading enough, no, spin has only two values. It is wrongly named. Okay? A qubit, physical qubit, is basically taking advantage of this quantum number called spin. Okay? Now, just again, you might remember this. Why can't I push this hand through this? Or why are you sitting on the chair? What is the quantum mechanical explanation for that? The electrons in the atoms here and the electrons in your butt, they follow the Pauli exclusion principle, which means what? Electrons of the two states cannot be in the same location. So it's Pauli exclusion principle that's preventing you from falling through the chair. Basically, the spin in a butt of your in a butt and this chair cannot be, and that's why you're not falling down. Okay, that's how strange this baby is. Okay, and it works. Okay, in fact, all of chemistry is basically figuring out the spin orbits. In fact, right, early Nobel Prizes were all given to show Mendeleev's table is a natural consequence of the fact that these spins can take only so many orbitals, right, and you follow Pauli exclusion principle. Just to give you, so spin is to me the central breakthrough of the last century, okay, from which everything got built. For us, it is a 2 by 2 matrix, okay, which can take on a value 0, 1 or 1, 0, and that's all we care about. Okay, it's a linear algebra. Decoherence means that a qubit cannot live by itself because there is ambient noise and it decoheres. This is where queuing theory and all is useful, because if you are sending a qubit in communication and it's getting buffered, because we know buffering, then the longer it stays in the buffer, the more likely it is to get decohered. That means by the time you receive it, it has lost its value, and therefore think of solving a queuing problem where as rho goes to 1, your waiting time goes up and your decoherence goes down. So if you look at the expected information, it goes up for a while and then collapses down, right, because rho goes to 1. That will be a paper in quantum communications. The difference is, what is the noise model? The noise model will have to be in the same space as the qubits, and therefore it will be like a 2 by 2 matrix. Okay? So if you read a physics paper or IEEE transactions in quantum engineering paper, and you say, hey, the man is sending a qubit and it's getting decohered, think of it as the man is sending a bit and it is getting old, it has aging in it, right? And the only thing is, instead of sending a 0, 1 and using Shannon theory, you're going to send this superposition thing, and that's called quantum Shannon theory. And the old age, which could be exponential, is going to be using some 2 by 2, depending on the type of noise. Okay, generalized amplitude damping and so on and so forth. Okay. So once you see that, you can start reading all these papers. So part of why Vikesh and I want to write this paper is first to say, hey, for you to understand those physics papers, let me quickly tell you what it is that they are doing. They're just manipulating vectors and matrices. They're in CN space. This is what that notation means. Okay. So two things that I never heard of until I got into physics. An outer product. Who doesn't know inner product? Everybody knows inner product, right? You take a vector, row vector, you hit it with a column vector, you get a number, right? We all know this, A dot B. What is outer product? You take the column first and then put the row. You get a matrix. I mean, it's natural. I mean, the point is, we never had a reason to know it, but that's the outer product. Okay. What is a tensor product? Takes a little bit while to get used to. Okay. Now, suppose you have a matrix multiplication, right? You have a matrix A, B, C, D. You have other matrix, E, F, G, H. What is matrix multiplication? You take this first guy, you multiply with that first guy. You take the second guy, and you multiply with this guy. Put it over there, right? That's the matrix multiplication, right? What is tensor? You take the first guy, you take this entire matrix and put it there. No, that's what it is. This guy, you take the whole matrix, put it there. You take this guy, put the whole matrix there, put the whole matrix there. This becomes a gigantic matrix. That's a tensor product. Okay? Instead of putting a star for multiplication, you put a circle and put a cross inside. It becomes tensor product. Okay? So what I'm saying is, if you know linear algebra, complex variables, probability, outer product, tensors, you are 95% there. Okay. Now, the Nobel Prize was given for this entanglement business. So this is what Einstein did not like about quantum mechanics. Okay. Once again, let's strip out stuff. what is entanglement? Suppose you have a state psi and you have another state phi. So basically remember a two vector, right? And you take a product of them, you get a state. That would be called a product state. Okay? No magic there. But it turns out you can actually write a state that you go back and say, who are these products? Who are its products? Not there. That is, you can create a 4 vector that did not come from the product of two vectors. Such a state is called entangled because you cannot separate it out into two things. In fact, this is the time they use the word correctly. Right? Now, entanglement has several counterintuitive features which Einstein called spooky action at a distance. Okay? Again, why does it come from? Who was the first guy who introduced action at a distance, knowing fully well it doesn't make sense, but he said, I know it doesn't make sense, but the math works out, so I just want to let you know I do not believe in action at a distance, but it works. Who was that man? His name was Isaac Newton. And Einstein, through general relativity, showed there is no action at distance because it is coming through, curvature, right? So that is why he called this spooky action at a distance, because you take an entangled pair, send them off to ends of the universe, and the instant you measure one, or its state becomes known, this guy's state becomes known with probability 1. And you say, but the time to take that information is way faster than the speed of light. How did it happen? That's what Einstein didn't like. Okay, EPR, right? Einstein, Podolsky, Rosen. Then a guy, for many years, quantum mechanics were, including the great John von Neumann, wanted to know if this was just a hidden variable theory. That is, if you had some more variables, it will become classical. Von Neumann, quote unquote, proved around 1928 that it cannot be a hidden variable theory, but his proof was wrong. The result was correct. A guy called John Bell came up with this inequalities, saying that if you violate these inequalities, then entanglement must exist. The 3 people who got the Nobel Prize showed experimentally, without a shred of doubt, that Bell inequalities were violated in experiment, hence the Nobel Prize. That entanglement is it exists. Now, why is entanglement important? It is because it allows you to send information in a secure way that classical computing cannot. It allows you to send more information. So in a classical information, you send some information, you take a second information, third information, it's additive. But you can actually have channels in quantum entanglement where the information you send is non-additive. So you can send more information more securely using quantum, hence the interest in quantum. Okay, and that is coming because of entanglement. So you will see around the problem number 3, problem number 4, problem number 5 in the write-up, we do entanglement stuff. Today I won't get into it because the kind of math is too much. Today my goal is to just get past one problem. Okay, that's what is happening. That is the interest in entanglement. Whenever people study baby problems, they study pure state, like I give you a state psi, and you know what it is. A mixed state is a mixture of pure states, but it's a mixture in the classical sense. P1 times state 1, P2 times state 2, P3, Pn times state n, where summation Pi equal to 1. That's called a mixed state. So the most general thing you will see in a quantum mechanics or a quantum information paper is start with a mixed state, which is a classical mixture of pure states, and all the math will be done on that, just to let you know. Okay, that's what is happening over there. What we know as probability distribution is called a density operator. This is what tells you something about these random variables. Okay, it's a matrix basically. I will show you the first problem. I think this is where SDP comes in. Something called positive operator value measure. I'll come to it in a few seconds, in a few minutes. What happens in quantum mechanics is every state evolves in a unitary fashion. And many of you may remember Shannon entropy, which is if you have a binary variable 0, 1, p times 1 minus p kind of a thing, p type log p plus 1 minus p log 1 minus p, then there is a von Neumann version of it using density operator. Okay? So think about taking Shannon theory classically and moving into quantum is called quantum Shannon theory. Okay? And that's kind of what you're going to see in the math. No Schrodinger equation here, because quantum information science is not studying it in that framework. There is an equivalence between the Schrodinger framework and the Heisenberg framework. In fact, what did Heisenberg call his framework in 1925? Matrix mechanics. But it just was so scary to physicists, because until then they hadn't heard of matrices. Right? Today, of course, how can you not know matrices? But that time they didn't know matrices. They knew differential equations. They knew Hamiltonians. Right? They knew how to work in phase space. They knew classical mechanics. In that sense, what Schrodinger did was present this new physics in the language that the older physicists could understand. He said, you know the Euler Lagrange equation. They said, yeah. Okay. Just put this in, it'll work. Replace energy with this I d by dt operator, momentum with du by dx operator, and shove it back in, and everything will work. Don't ask why. And it worked. That's the first quantum mechanics. Independently, Heisenberg was trying to explain the split, experiment, double slit. And he thought the matrix formulation was better. Now, von Neumann, being a smart guy, saw all of this and said, okay, let me put it in a firm framework. So the framework we use now is 1929 von Neumann, who put it all in the framework of Hilbert space and Cn and matrices. Okay, so that's what is happening here. No special relativity, because we're not going the speed of light, nothing is happening. I'm not in quantum field theory, no Dirac other than his notation here. Okay, so what I'm saying is quantum information science is actually the simplest quantum mechanics you can do. Okay, of course there's no general relativity because there's no gravity. Okay, what I'm saying, there's no special relativity either. Okay. What happens is, you remember there's something called eigenvalues and eigenvectors in matrices. Now this is what will blow your mind. This is when I say don't ask, just do it. When we think about classical physics, a body has a momentum, mass times velocity, right? Or it has some energy, kinetic energy, half times mv squared, right? Remember all this stuff, right? Some continuous thingies, right? Not so with photons and electrons. Energy and momentum, what we call energy and momentum, or what physicists call energy and momentum, are basically matrices. You say, what happens with the matrix? So it has a matrix A. A matrix A has several eigenvalues. Yeah, what is an eigenvalue? Ax equal to lambda x, right? If you can write x, those x's are called eigenvectors, and the lambda is called an eigenvalue, right? How do you find these lambdas? You write the characteristic polynomial, right? A minus lambda I determinant, set it to 0, right? In quantum mechanics, the energy that this particle can take can only be one of these eigenvalues, and it can only take one of these eigenstates. That's what makes it quantum. So, whatever happens when you measure the energy of the system, it is going to be one of the eigenvalues. It is going to be in one of the states given by the eigenvector associated with that eigenvalue. The probability that you will find that eigenvalue for its energy and that eigenvector state is the square of the amplitude of that state that you measured. That is quantum mechanics. It's all about eigenvalues, eigenvectors, unitary matrices, determinants, taking traces, and so on and so forth, and interpreting it this way. That's so what I'm saying is I'm trying to demystify quantum mechanics to the fullest extent. So, pre-measurement, this matrix evolves with time, either because you wrote the algorithm, do this, do this, do this, do this, or because it's hanging out there and noise is hitting it. But at some point when you measure it, whatever state was at that instant of measurement, it collapses to one of these eigenstates with the probability. Okay, that's what's happening here. Okay, as I said, Heisenberg actually called it matrix mechanics, which is the right word. By the way, there's another word you may or may not have heard of called wavicle. Have you heard of this word called wavicle? W-A-V-I-C-L-E. It's odd that even physics guys haven't heard of it. Remember, when quantum mechanics was being created, there's confusion. Is it a particle? Is it a wave? Sometimes it behaves like a particle, sometimes it behaves as a wave. Is a wave particle duality? You got the de Broglie result. Everything is a particle, everything is a wave, blah, blah. So, there was a physicist, Arthur Eddington, who said to avoid thinking of it as a point particle or avoid thinking of it as a wave, which are classical, let's create a new name called wavicle, because it becomes very clear it is a new thingy. But physicists didn't like it. Okay? I actually like it. So, if I ever write a book on physics, which nobody will read, I will call it wavicle physics, because that is what it is. But once I tell you it's a wavicle, you are no longer confused. You don't think like Newton, right? You don't think like Huygens or whoever who was doing wave, right? You know it's a new thingy which is given by this mathematics, right? So, what you have is inner product of a column vector, you know how to do this. Because things are in complex world, you have to worry about complex conjugation, yeah? Right? Whenever you take the transpose, you have to put the minus on the I side, okay? You got the norm vectors, you got orthonormal basis, then the bracket notation basically is the ket is a column and bra is the row. It's called the bracket notation, okay? And a ket, if you inner product itself, you get a pure state, it becomes a 1, okay? So, all I'm saying is you look at the words like Dirac notation and pure state, it might scare you, but in your mind you say it's undergraduate linear algebra. Every physical variable which are observables are Hermitian, which have other properties, right? Determinant is 1 and all the good stuff, right? I say matrices in brackets because if you are a picky physicist, you will say, well, there is a difference between an operator and a matrix. It is, because you have to choose what is called a computational basis, okay? If you take your basis as the 0, 1 and 1, 0, you get a matrix. You can choose a different orthonormal basis actually as your computational basis, like a Bell state, set of Bell states and orthonormal basis. And if you write the matrix for that Bell state, the numbers inside that will be a different matrix. The point is, the matrix elements depend on the computational basis that you have chosen to work on. Okay? But at the level of our discussion, let's say we're working on simple computational basis. Think of any time you read operators as basically a matrix. Okay? There's something called a spectral decomposition, which again, projective decomposition, again, all straight linear algebra, right? There's nothing new here. What is new here is to say, if the observable O is measured with a system, then it obtains an eigenvalue lambda I with this probability, which is basically taking the square of the amplitude. Trace is looking at the diagonal elements. Okay? This is called Bond's rule. He has a Nobel Prize. Okay? I remember there was one statement made by Dirac. I don't know if he was inordinately modest or simply downright honest. He said the 1920s was a golden age for physicists because second-rate mathematicians could do first-rate work and get Nobel Prizes. If you look at all the Nobel Prizes from today's mind, they are trivial. But at that time, there was so much confusion. And people didn't know matrices and vectors, but for them to introduce it was like, oh my God, Schrodinger Nobel, Heisenberg Nobel, Born Nobel, right? Dirac Nobel, go, go, go. And then he'll back and say, wait a minute. Come on, right? So let's solve a problem in quantum information science. The simplest problem that Vikesh thought could be introduced is called the quantum state discrimination. It goes like this. In classical physics, if you have a state A and a state B, you know either they are the same or they are not. There is no problem of indistinguishability. In quantum, that is not the case. Okay? So what happens is, suppose you have random variable x, ordinary random variable, right? And it can take, let's say, you throw a dice, 1, 2, 3, 4, 5, 6, probably 1/6. Okay? If you get a number 3, you will create a quantum state sigma 3, okay? Which is one of those kets, right? Some call it, C3, B3, something like that. Now, the key task is to measure the prepared state and predict AI. So what happens is, I throw a random variable x, I get a 3, I create sigma 3, I give you Mabel sigma 3. I wanted to measure sigma 3 and tell me, oh, Sridhar, you got 3. Okay? I might give you sigma 4. You tell me it's 4. And so on and so forth. So your success probability is, you tell me the probability that y is I if x is I, in case it is I, right? And if you do it correctly, this should be 1, summation pi will be 1, p success should be 1, right? I mean, right? So now the question is, in quantum, how do we do this measurement to maximize PS, okay? Probability of success. Now comes semi-definite programming. A collection of matrices, operators, are positive semi-definite and sum to identity are called a positive operator value measure. Okay. Any given measurement on a quantum system can be described using a POVM. Our goal is to find the best POVM that gives PS equal to 1 if possible. Okay? That is, and associated with each I, you get this probability. And so rewriting P, trying to find PS becomes a semi-definite program. So to calculate what is PS is equivalent to saying, find me the POVM that maximizes the PS. quantum state discrimination is basically SDP. Okay. For simple problems, suppose I'm in 2 dimensions, I toss a coin, I get only 2 values, and with probability p, I get value 1, q, I get value 1, and with the other, I get 2, and with the first, I create the state 1 0 0 0, and the second, I create that state. Then for these simple things, you can actually don't have to do SDP. You can calculate, the POVMs are this, and so on and so forth, because they're algebraically possible. But the minute I give you n-dimensional space and d-dimensional qubits and tell you, okay, give me a POVM that maximizes the probability of success, and can you show me that the probability of success is 1 or not, you have to do an SDP. Okay. So hopefully you can see now how SDP come in. SDP come in because of the POVM. Okay, that's one way they come in. Okay. What we did in this write-up was we gave the quantum mechanics the bare minimum. I skipped quantum information science bare minimum because I didn't want to go through all the von Neumann entropy and Halevo bounds and all that. I went into QSD where this is introduced. Right? These closed form solutions are given. But we also created a Jupyter notebook. If you go to GitHub, which is why I wanted to go here. So if you click that link, you will come to this GitHub page. Actually, you will come to one GitHub page before this. Okay, notebook 1. And we have written all the Python code so that you can check that for these toy problems, if you numerically solve it using SDP, you will get the same answers. You get 1 or 0.99999 like that. Okay. So what we wanted to do was say, hey, let's introduce quantum information science using matrices, introduce the Dirac notation, take a sequence of problems that are slowly increasing in complexity, QSD being the simplest, show what the closed form solutions look like, but also give you a computational code so you say, no, I want to press a button, I get the same answer. And because after a while the problems become hairy, there are no closed form solutions. Okay. So here we have embedded all the solvers into here, and you can take the same example that is there in the textbook, and you can rewrite it this way, and if you run the program, you'll get that the probability of discriminating is 0.9999. Basically, it's 1. Okay. So what we want to do in this tutorial was to give you both the introduction to these problems, the cases where the closed form solutions exist, recreate those closed form solutions in Python, and then give you the ability to write your own SDPs you want to solve. Okay, so then you say, okay, I want to solve a different SDP. Everybody good with that? So you can go to quantum state fidelity. It's another problem. If you're given a mixed state and another mixed state, and you want to know what is the overlap between them, you can formulate that in a variety of ways. Those of you who know statistics very well might know something called the Bhattacharya distance and so on and so forth. There's a linear algebra way of doing things, but it's much more natural to write it actually as an SDP. Okay. So second problem is quantum state fidelity, where you're given one mixed state and you're given another mixed state, and you want to know how much is that overlap. Okay. and that becomes an SDP problem. Okay. I'll mention a third one briefly before I close it out. And it takes us to channel, and this takes us into cryptography and secure messaging, and quantum, kind of message systems. So suppose I send Mabel a density operator. Then Mabel measured something, and based on that measurement, she takes the density operator into that channel and sends it back to me. I measure it, and I want to know what Mabel measured. It's like the quantum state, except that x is not a random variable, but it is a full state, and what is measured is not a state, but a channel, a quantum channel, and back. Okay. This is called quantum channel discrimination. That's problem number 3. That's when you start getting into real quantum information science. Here, the question is, what should be the density operator I should have sent you in the first place, so that when you do your thing and send it back and I measure it, my probability of success is very high. Right? It is a search over the density operator that I should have sent you in the first place, hence it becomes like an SDP. You go through the tutorial, you will notice that for problems, if you don't use entanglement, the probability of success is going to be strictly less than if you use entanglement. You'll see some examples of that, which shows you why entanglement is a key resource in quantum information science. In fact, one of the worst case bounds that are shown there is, if you don't use entanglement, I can create a d-qubit in such a way that my likelihood of getting the answer is not that much better than half. But if I use entanglement properly using SDP, the probability of success is 1. Like the most dramatic kind of use of entanglement as a resource, because then we can communicate, right? And I know exactly what to do. So again, the application is secure quantum communications. Right? Now, why is it called secure? Because a unknown qubit cannot be cloned. There's something called a no cloning result. So see, if you're sending bits, somebody can just copy the bit, right? And your bit will come to you, and that person has a bit. You can't do that. You can't clone it. And the instant somebody touches your qubit, what happens? I know you touched it. That's what makes quantum communication secure. You can't copy what is unknown to you, and the minute you touch it, I know you touched it. And then I want to make sure, because of super additivity, that I'm able to send more information, and then through entanglement, I'm able to understand what you're saying perfectly. That's what makes quantum communications so sexy and fundamentally different from classical communication. That, in my view, is where much of the progress is being made. You'll probably hear stories about China was able to transmit signals 20 miles away, right? Or in the US, they want to do it 10 miles away, right? And now, why is the distance a problem? Because things are getting decohered. What happens in standard communications over long distances? What do? We amplify. Get a signal, we amplify it, we send it out. There is no quantum amplifier yet. The number one research being done is, can we build these quantum repeaters? Can we build these quantum amplifiers? Right? And if you can build the quantum amplifiers, then things are happening. Right? That's what's happening over there. And then there are people studying different kinds of mathematics on what kind of repeaters you can make, and so on and so forth. So again, think of it as classical communications, but now working at a whole different level of what you're trying to send, basically. what was it, Ting Long? Thank you. So you got quantum state fidelity, which was the Bhattacharya distance I mentioned, quantum channel, which is what I said. Then there is quantum entanglement and separability, and then once you start getting to problem 5, you will be kind of indifferent from a physicist, because that there's epsilon degradability, and you start reading papers of Shore and Bennett, and you get over there. So our goal was, in about 5 problems, we get you to a place where you can actually understand what Bennett and Shore are trying to say. Okay, but my view is a guy like me can understand 1, 2, 3, which means that you can understand 1, 2, 3, 4 for sure. Okay, remember, I'm a business school professor who sells software. Okay, not really the deepest guy in the world, right? Now, why SDP? Because canonical problems, several is SDP. In my view, this is the entree for our field. In fact, yesterday or day before, Davide Venturelli was in Pittsburgh co-teaching, and he said, "Hey, Sridhar, did you see this? I got this note." And I said, "What note is it?" He says, "There's a new book coming out, November 2022. You know what the book is called? Semi-definite Programming in Quantum Information Science, $193. Written by 2 physicists, one from Catalonia and Barcelona and somewhere else, some physics departments. Okay, so this is it. This is the book that's coming out. What I'm saying is, yes, even the physicists have figured out that the book they should write is how to do QIS using SDP. Okay, typically they don't possess algebraic closed form solutions. And when you read papers on arXiv, you can see that they don't think like computer scientists. They don't think like us that says, well, come up with this rule and we can show this bounds, and if you do this, this is a 2/3 approximation to PS. Right? I mean, that kind of constructive graph proofs that we have, right? They don't think like that. But if you look at it, that's what they're asking for. They don't know, is PS 1? What is the lower bound on PS? What is the upper bound on PS? They don't know. Can you come up with a easy to understand rule and give me its worst case performance? That is, if you look at their papers, they're asking for people in computer science in some sense to give them the answers, right? Other than pressing buttons and hoping that they get 0.9992. Right? Beyond SDP, it turns out, as a direct, there are this von Neumann entropy I mentioned, and there are other objectives they care about that actually can be approximated using SDPs. But to approximate them using SDPs, the state space explodes for the accuracy that you need. Okay, and for those, we need some computationally effective methods. So to me, SDP gives an opportunity for theoreticians to contribute by coming up with nice bounds and easy to understand algorithms with good performance, or it can help people who like computational work because you want to solve large size problems. As I said, I like Susskind's book, The Theoretical Minimum. Starts with spin. Read it slowly. There are a couple typos I sent him so that he can correct it. If you say, I don't want to talk to physicists, there is a great book written by 2 computer scientists called Quantum Algorithms via Linear Algebra. In fact, their opening is, we refuse to use Dirac notation. It's only matrices. I think they use Dirac notation only to say, look, I'm doing it, I'm just doing it. But it's written by computer science guys, okay? And then I mentioned David here, Venturelli, Davide, and myself. We created this quantum integer programming that is available on GitHub. All our notes are there, all our videos are there, all our GitHub programs are there. Now, when I was young, there was something called Shom series. Have you heard of this? Right? It doesn't teach you physics. It teaches you how to solve problems in physics that come in exams. I mean, they're 2 different things, right? Right, I understand, okay, because I have A+ in all the exams, okay. And it doesn't mean I understand physics. I just know this is the question, this is the answer, okay. The Shom series, okay. So the Shom series equivalent of this is this book called Steeb and Hardy, Problems and Solutions in Quantum Computing. I mean, they have taken like 25 chapters, like 20 questions, 500 problems fully worked out, okay, fully worked out. All 2x2 matrices, 3x3, 4, everything done, okay. So if you ever look at things and say, I don't know how to solve it, just open this book, okay, solution is there, okay. This is for Shom series people to say, just give me the answer, right. And then Eleanor Rifle, I think, is the head of the quantum AI lab, at quantum and AI lab at NASA, right, where David, you work, right. And she has, I think, is a mathematician, but she's a little bit of a physicist now. Pollack, I think, is a computer scientist, and so they've written this book called Quantum Computing: A Gentle Introduction, and I use the word gentle in my title because of that book. So I'm basically saying thank you, Feynman, thank you, Susskind, thank you, Eleanor Rifle. Okay, and that's it. That's the end of my talk. Any questions, comments? Yeah, go ahead, Javier.
Can you tell us about the size of the SDPs that would be interesting to solve, say, today? Where, maybe something that would be that would shed light on some interesting quantum computing problem. How are we within reach of, say, taking just, say, an expert in SDP? I can take some algorithm and say, okay, I can already help someone in quantum computing.
Yes, in quantum sensing, I would say yes.
So how large are these problems, if I may ask?
I don't have the paper in front, but it grows very quickly because it's a if you have a n qubit problem, the state space becomes 2 to the power n. So 10 qubits, and you're trying to get to that, become 2 to the power 10. So you get to be 2 to the power 10, 2 to the power 20 very quickly. But I can give you references. I think in the paper there's some references from the size. So I think the computational aspect, there is some benefit. But I'm also suggesting that there is maybe a greater intellectual contribution that can come from this theoretical bounds and coming up with clever algorithms, rather than solving SDPs. So those are the two things I think about.
Thank you.
Yeah.
Any other questions from the audience?
Well, I hope it was useful, that you learned something today, and quantum information science is less scary than it was before it came in. Okay? Thanks, guys.
All right. Yeah. Thank you, Shrida, for a very interesting introduction to quantum.